So this next topic is proof, and how we set out proofs and the abbreviations and the words and the techniques we use become very important, and the structure underneath it is this structure of logic. Logic is an actual branch of mathematics, and so there are certain rules that we follow and so on. It actually is also a part of philosophy. So let's start with some terms. First term is what we call a proposition, which is simply a sentence that proposes an idea, and that idea can simply be either true or false. Can't be both. There you go, an example. It is raining. That's a proposition. Is it raining is not a proposition. That's a question. Okay. So logic has its own language that we use. Because what we do is we get these sentences and we bring it back to just symbols, basically, and use symbols to solve it. So the alphabet consists of what we call propositional variables. Basically just looks like pronumerals. So you go some examples: P1, P2, Q, X, Y, and of course, what's the last one I put? It's a capital Phi. Yeah, that's a capital Phi. Then we have punctuation symbols, much as you do in a normal alphabet. Basically, our punctuation symbols are like the parenthesis symbols, so the grouping symbols. Then we have logical symbols, these things that are called the connectives, which connect these propositions together. So the arrow, or the double arrow more correct, to the right is implication. This implies this, and we use those for if-then statements. If this happens, then this will happen. Two different ways of doing negation. So there's the tilde, or the, what would you call that? An L on its side, fallen out, whatever. That symbol. And it's the complement of a proposition. Remember, it's either true or false. So if it's true, its complement is false, that would be the negation. It's the opposite. Then you have the double-ended double arrow, which represents equivalence. So these two propositions would be logically equivalent. It's like saying the same thing. That's and, so that's the conjunction of two propositions. Both things would be happening. And then we have or, disjunction. This happens or this happens. Notice very similar to what we see in set theory, except these ones are sharp. So intersection and union, which also represent and or in set theory. Then we have our quantifiers. So the backwards E represents there exists, and the upside down A we use for all. And you see me use the for all one in induction, because obviously that's a type of proof. Okay. So statements. So we want to make statements. What are they? Could simply be a proposition. A proposition in itself is a statement. Or it might be a series of propositions that we've joined together using our punctuation symbols and our connectives, our logical symbols. So what is a logically valid argument? It's a list of propositions from which a conclusion will follow. That basically is a proof. So that's what we call a proof. I guess the first type of proof you saw was in geometry, and that's exactly what you had. Remember, you listed all the information. These are all the things we knew. All vertically opposite angles were equal. Angle sum of a triangle is 180 degrees, and then you finished your proof by proving something. You say, oh, well, therefore, this must be true. That's basically a logically valid argument. Now, this is not an example. This is defining the word example. Okay, so example, that's a situation that will demonstrate the assertion of the proposition. But then we have these things called counter examples. And counter examples will demonstrate this proposition is not true in general. And we often use them to disprove something. Because all you have to do is find one case where it doesn't work. That's what we call the counterexample. And then we know the proof is no good. So we use it to invalidate the argument. Okay, so let's talk a bit about negation. So the negation will change the logical value of the statement, because it's the opposite. So if it was originally true, if we negate it, it becomes false. And the other way around. Okay, some rules with negation. So x and y are representing some statements. So the negation of x and y is equivalent to saying negation of x or the negation of y. Okay? Because what you're basically saying is we don't have x and y. So therefore we must have either we don't have x or we don't have y. So they are equivalent statements. Now, the other way around, the negation of x or y is logically equivalent to having both of them. So negation of x and the negation of y. Again, if you think about it, I don't have x or y. Well, therefore, I don't have x and I don't have y. All right, this one's an interesting one. The negation of for all x, then ax is just representing some situation that x might obey. Might be that x is an even number or something like that. So for all x, x is an even, would be equivalent to saying there exists an x such that we don't have ax. So that's what we say there. If we don't have the situation that for all x, every single possible value I could substitute into this thing, I get this a, whatever a is. So we're saying if we don't have that situation, well, the only way we could have that situation if there exists a value that we could put into a and it would not be true. They are logically equivalent. So the negation of for all usually ends up being there exists. That's sort of like the link you're looking for. Over here I said for all, then I got the there exists. And the other way around is true as well. The negation of there exists, because if what we're saying is that situation is not true, there does not exist, is basically what we're saying. Because it's the negation of there exists an x such this thing is true. So we're negating that. So in other words, for all values of x, there's no x I could find that this would work. So for all values of x, I don't get ax. They're logically equivalent. Okay, so let's look at some examples. X, my statement simply is the number is even. The number is even. So 6 would be true. That is an even number. The negation of x would be the number is not even. Notice it's not the number is odd. Because of course you can have fractions, you can have negative decimals, you can have all sorts of things. So the negation is not that it's odd. It's simply that it's not even. 6 would now be false. So the negation changed the value of it. Why? All birds are black. There's my statement. The negation would be at least one bird is not black. I mean, there would be other ways of saying it. That's just one way of saying it. But that would be the opposite case. If I don't have the situation of all birds are black, then I must have a situation where there's got to be at least one bird that's black. So that would be the negation of it. Another way I could say is, not all birds are black. Another way I could say it. Maybe some birds are not black. Okay, let's have a look at this one. Z is my statement. There exists an x which is an element of the real numbers. So I'm only thinking about real numbers. Such that x squared is less than 0. Right? So I'm saying there exists an x, belongs to the real numbers, such that x squared is less than 0. Because remember, these are just statements. They don't have to be true. And in fact, that one is actually false, of course. But that's what we're basically saying. There exists a real number such that its square is negative. Essentially, that's what I'm saying. So the negation of that would be for all x, again, that belong to real numbers. Notice I don't say such that there, I just put a comma for this one. X squared is greater than or equal to 0. That would be the negation of that. So for all real numbers, their squares are greater than or equal to 0. That of course is true. So the negation of my false statement became a true statement. Implication. These are our if-then statements, the heart of deductive proofs. P implies Q. If P is true, then Q must also be true, because P implies Q. If I have P, then I must have Q. P is what we call the premise. So this is our premise. Q is our conclusion. So P implies Q. Now P, now you might remember these words, sufficiency conditions and things like that. So P is a sufficient condition for Q. Because if we have P, we know we must have Q. So just knowing P is sufficient enough to know we have Q. Now, Q can still exist without P. However, if P does exist, Q must exist. So necessary conditions is the other way around. Q is a necessary condition for P. Right, so P implies Q. Q becomes necessary for P to happen. So P cannot exist unless Q exists. Because if Q does not exist, because remember, every time I have P, I've got Q. P implies Q. So if I don't have Q, then I can't have P. So it becomes necessary rather than sufficient. Alright, there we go. X. You score 90% or above in extension 2. There's our statement. Maybe true, maybe false. Let's hope it's true. Y, this one better be true. Y is the statement, you always listen to your teacher. X implies Y. That's what I'm saying. If you scored 90%, you'd listen to me, okay? X implies Y. So, scoring 90% or above is sufficient to conclude that you always listen to me. Okay? That's sufficient. However, it is necessary to listen to your teacher to score 90% or above. So let's go back to this. If P, Q can still exist without P. So in our one we're saying Y could still exist without Q. So it is possible that you always listen to me, but you don't score above 90%. That is a possibility, you see. Hopefully this won't happen, of course. Now, the negation. The negation of P implies Q is P, you have P and you don't have Q. Because P implies Q. So if we don't have P implies Q, then we end up having P, but we don't have Q. So we have P and we don't have Q. Basically we're saying it meant P did not imply Q. Alright, converse. Converse. It's the reverse of the implication. It's like reading the implication backwards. Okay? So the converse of an implication, reverse it. So the converse in P implies Q is Q implies P. That's the converse. And there's lots of theorems where both of them are true, but they're not always true, both of them true. I've probably got examples here, so let's just go through it. The converse of a true statement may or may not be true. That's what she's saying. Similarly, the converse of a false statement may or may not be false. Okay, here we go. X is the statement, it is raining. Y is the statement, the grass is wet. Now, it certainly might be true that X implied Y. It certainly implied it. It is raining, the grass ended up being wet. Because it rained, the grass got wet. But it's not necessarily true that Y implies X. The grass is wet does not mean it's raining. It might be early in the morning, the dews come up, the grass is wet. Someone might have turned the sprinkler on, grass is wet. Equivalence. Okay, these are these if and only if statements, spelt IFF. That's the abbreviation for if and only if. That means both are true. P implies Q and Q implies P. And that's why we have the double arrow, because the implication's going both ways. Okay? So two statements are equivalent if each is the consequence of the other. If we have P, we get Q. If we've got Q, we get P. Example. X is a statement, A, B, C, D is a parallelogram. Y is a statement, the diagonals A, C and B, D bisect. Right? So it is true, X implies Y. Yeah, if it's a parallelogram, we can conclude that those diagonals bisect. And Y does imply X. Yeah, if I've got a quadrilateral and I know the diagonals bisect, I can conclude that's a parallelogram. So they are equivalent statements. So we could write it that way. Actually use the word IFF rather than just if, and then we know, oh yeah, this works both ways. Alright, this one might be new. Contrapositive. contrapositive. The contrapositive of the implication, you get that when you negate the converse. When you negate the converse. So in other words, what we're saying, if the original statement is P implies Q, the contrapositive of that is the negation of Q implies the negation of P. So you negate going back the other way, the converse. And they are equivalent statements, and that's great because in proof, sometimes if you have to prove P implies Q, it actually is easier to prove not Q implies not P. And so you go and prove that, and then you can say, oh well, therefore it must be true by contraposition. So an implication is logically equivalent to its contrapositive. Okay, so here's an example. X, a polygon is a triangle. So we know a polygon is a triangle, that's a statement. Another statement is, oh well, the interior angle sum is 180 degrees. So we do know that X implies Y, that's certainly true. If a polygon is a triangle, then the interior angle sum will be 180 degrees. We know that. Well, let's have a look at what the contrapositive would say. Negate the converse. So if the interior angle sum is not 180 degrees, that's negating Y, then the polygon is not a triangle. Well, that's certainly true. So you see how they're equivalent statements. So X implies Y is equivalent to not Y implying not X. There is these things called truth tables. Now before I start on truth tables, let me tell you this. Truth tables are not in the syllabus. Don't know why. I do not understand how you could do any course on logic and not include truth tables. Okay? So I'm going to show you about them, and you might find them handy sometimes to work with. Truth tables. Here's basically our table, our rules that we can use. So here's all the different things we could have. I've got two statements, P and Q. I could negate P, well I could also negate Q, but the column would be the same for what I'm about to do, so I just put that there. We could have P and Q, we could have P or Q, we could have P implies Q, we could have P is equivalent to Q. Yep. Here are my two statements to use as an example so you can see how this table works. So P is simply going to be a statement, the cat is white. Q is the statement, the dog is black. Okay, these are two statements. If both of these statements are true, so we've got true and true, well the negation of P would be false, P and Q would be true, P or Q would be true, P implies Q would be true, and P being equivalent Q would be true. So if indeed the cat was white and the dog is black, all of those things would be true statements other than the negation of P. But if the cat's white but the dog wasn't black, cat's white but the dog wasn't black, then not P would become false. Right? Because we're saying not P, we're saying the cat's not white. Well, I just said no. We're saying the cat is white, so negation changes the value. But let's have a look at P and Q. Do I have both P and Q? The cat is white and the dog is black. Well, no, I just said the dog was white. So remember we said Q was false. Therefore, the statement P and Q must be false. P or Q, however, would still be true, because we say the cat is white or the dog is black. Well, the dog's not black, but we do know the cat is white, so this is still true. P implies Q would now be false, because we have P, but we don't have Q. So P does not imply Q. Remember, Q was a necessary condition for P. And P being equivalent to Q, well, no, because they're not both true. No good. Other way around. Let's say P is the false one. So the cat's black now, but yes, the dog is black. The negation of P would now become true. Well, the negation would be the cat is not white. Well, no, I just said it was black. So that is now true. P and Q would be false. P or Q would be true. P implies Q is now true. Remember, when it comes to P and Q, P was a sufficient but not necessary to have Q. So it is possible to have Q without having P. So the fact that the cat's not white does not stop the dog being black. So P implies Q still becomes a true statement. P being equivalent to Q would be false. Well, what if they're both false? What if it's the other way round? The cat is black and the dog is white. So the negation of P is now true. P and Q, again, would now be false. But P or Q is false now. I don't have either of them being the right way around. So that's false. P implies Q is now true. Because the negation of Q implies the negation of P. It would be true by contraposition. And is P equivalent to Q? Yeah. That is now there. So that's basically, so there are the examples I use, but that gives you the values of what you could apply to a truth table in these situations. So now it's time for you to play, because you'll notice I did not put the answers down for this example. I'm leaving it for you guys to see if you can work out this little logic problem. 3 students, Alfred, Kurt and Rudolph, are accused of stealing and selling copies of the exam. Now, there was an inquiry and they testify. So these are their statements. Alfred said, well, Kurt is guilty, so he's dobbed him in. And Rudolph over there, well, he's innocent. He didn't do anything. Kurt said, well, look, if Alfred is guilty, then so's Rudolph. They're guilty as well. And Rudolph said, hey, I'm innocent. I did nothing. But at least one of the others is guilty. So these are the 3 things they said. So how do we break this down and solve it using logic? Okay, now here are your questions you have to answer. Is it possible for everyone to be telling the truth? Is that possible? If everyone is indeed innocent, which one of the 3 lied? Someone there must have lied. Now let's assume everyone's telling the truth. Who is the guilty person? 4th question. All right, oh yes, this is a good one. If the innocent people tell the truth and the guilty people lie, who's guilty? Kind of makes sense. If you're innocent, you tell the truth. If you're guilty, you're going to lie. So if the innocent people tell the truth and the guilty lie, who is guilty? Righto. Let's see if you can work this out. I'll turn this off because so I've basically got 3 propositions, which basically I'm just going to say these propositions they're all guilty. So proposition A is Alfred's guilty, K is Kurt is guilty, R is Rudolph is guilty. Because I'm pretty confident someone's guilty. Okay, I'm going to draw up my truth table. A, K and R. They're all the possibilities we could have. If you think about it, we're saying how many ways could we arrange these? So either being true or false. It sort of goes into perms and coms now. But that's how many we end up with. So let's break the statements down. So Alfred's statement would be that. Kurt is guilty and Rudolph is innocent. So Rudolph being innocent is the negation of Rudolph. True, false, false, false. I'm just reading off the K column. The negation of R then would change the value of the R column. So they would be all the R ones. So now I'll go back to that table we drew up, which gives us the code on how to solve this. Well, these are the only ones that end up being true in that table. It was if we had true and true, then it was true. All the others, false. Okay? So I now know that about Alfred's statement. Depending on those scenarios, he might be telling the truth, he might not be telling the truth, depending on whether these other things are true or false. Kurt, A implies R. If Alfred is guilty, Rudolph is guilty. Again, let's fill down the column for A and R. They were all the values. Now let's have a look at our code. A implies R. Which ones are false in that situation? Because they had a smaller number. True implies false was false. Okay? All the others are true. Okay. Rudolph's was a bit more involved Rudolph's statement, the negation of R, because he said, oh, if Rudolph is innocent, right. So we have Rudolph being innocent and we have either A or K. So that's basically how we would write Rudolph's statement down. So let's fill in. Okay, R is the negation of R, so I change the value of R. A, write down the value of A. K, write down the value of K. It's still mathematics, so you always do your grouping symbols first, inside the grouping symbols. So we have a look at the A or K. Which ones of those are true, which ones are false? Well, false or false became false, the others were all true. So now I'm looking at these statements, the ones in blue, and the not R. So now I'm looking at the A table, and I fill that one in. Those three would be true, because we have true and true, true and true, true and true. All the others would be false. I now have a completed truth table and I can answer the questions. So the first question was, is it possible for everyone to be telling the truth? The final answers I've put in red there so they stand out. I'm looking for 3 T's. Can everyone be telling the truth? There it is right there. Yep, it's possible. It's possible all 3 could be telling the truth. Okay. If everyone is innocent, who lied? Now this one's a little bit trickier. If everyone is innocent, who lied? Okay, the statements, remember, they're all guilty. So who lied? There. I basically want this one here, because if all of these values are false, we're basically saying these 3 statements are all wrong. So that's the row I'm looking at. So who lied? I come along and see, well, whose statements were false? Well, Alfred and Rudolph lied. Assuming everyone's testimony is true, who is guilty? So I'm not saying the statements are true, I'm saying what they said was true. Who is guilty? And it's that line there, because we're saying everyone's testimony was true. So I'm looking for 3 T's. Who is the guilty party? T. Kurt. Kurt is guilty. Then the final one, if the innocent tell the truth and the guilty lie, who is guilty? And it's that row there. It's that row there. If the innocent tell the truth and the guilty lie. So the innocent people would be, we're false. So where there's false, their statements must be true. And the guilty lie. So where we see true, their statement must be false. And that's what we're looking for, and that's the situation. So Alfred and Rudolph would be guilty in that final situation. We'll have a go at exercise 2A.